Okay, so again, Mike Walmsley with TE Connectivity. We're going to talk about interconnect standards today, everyone's favorite subjects. So connectors from a system design standpoint, they degrade the signal in your system, they add physical space and considerations and cost. So nobody really likes connectors, although in a modular system, they're an essential component of them. And standards, developing standards, for those of you who've been around it, they can be quite challenging with multiple companies coming in with solutions, trying to agree on content within a standard, going through the draft, going through the ballots, the comment resolution. Can be painstaking work. But actually in interconnect standards, I'm going to show you what's going on within the standards. It's a really an exciting time because there's a lot of new exciting solutions that are coming out. So I'm going to cover key drivers, status and trends in interconnect development, how can we accelerate connector standardization and implementations, and then what are the next challenges and opportunities that we see. So if you look at industry drivers, it's a lot of things we heard about yesterday, faster processors, more cores, need for more I/O count. SWAP is as relevant today as it ever has been. Open systems architecture, Roger did a good job laying out SOSA and the drive from the military branches up through the industry to standardize solutions. And the modular scalable solutions like VPX are very predominant in our industry. So you may be looking and thinking, those bullet points look familiar. Didn't Mike present those 3 years ago at ETT? Well, yes, I did. So the point being that really at a high level like that, those industry drivers are still the same. What changes is the bar. So 10 years ago, we'll still be talking about SWAP, but we'll be talking about it from a whole new level. So when you have industry drivers, they drive technical solutions in the industry. So whether you're a component manufacturer or you're a system developer, you're going to drive solutions. Your next-gen solutions are going to address some of the drivers that I've talked about. When you get into fruition on your solutions, you get some early adopters, you get some sponsors, you can develop standards around those. Once those standards are evolved and released, the market develops. You build that ecosystem, they get proliferated across many different applications. So standards are an increasingly important part of the technology changes that we have today. So I'll give you a couple examples. So speed, several years ago, we were approached to do the next generation protocols, 100 gig Ethernet, PCIe Gen 4. The VDIF46 connector that was originally released couldn't support those speeds. So the challenge was to create a connector that was intermatable, backwards compatible, that met those additional speed requirements. So over a 3+ year period, we developed that. We developed connector models, channel models, worked with key industry partners, and developed the RT3 connector, which we launched a year ago. From a standards perspective, those are being adopted into 46.30 and 46.31 for a solder tail variant of that. And as we get those into those standards, they get adopted into slot profiles, or module profiles, they are implemented then in those next generation solutions. And it builds the volume, builds the ecosystem. Another example, density. This slide may be familiar to you from previous ETT presentations, because 3 years ago we looked at this and said, okay, in a 3U VPX slot, how can we get more RF, more optics, not infringing on all the digital space that we have available to us. So that view is the same as what I presented, I think 3 years ago. The difference is the standards that are added to that slide. So you could see we've taken that concept that was developed, we've built product, we've worked through the industry and through the standards organizations, and we have standards in draft or release to support those. So this basically shows the original RF module and with an SMPM interface that has 4 RF contacts in it in a half module. It shows a single MT in a half module, and it shows a P1 connector and a P0 connector. So what we were doing there is looking at how can we package those in higher density platforms, and we took the nano RF, which we developed, put that into a half module with 12 contacts. We've taken the MT, doubled the density, putting 2 MTs in a half module, and being able to shrink some of that space that gets that RF and optical density so that we have space for the digital and we can upgrade the VPX connector to the 25 gig solution. And on the right is the hybrid that's been shown that we are working on today. And I'll talk a little bit more about that as well. But so predominantly in the original RF world, where you have those 4 contacts in that half module, if you wanted 12 RF lanes in your card, you'd be using up more than half the card. It would take a module and a half to do that. Now, today, we can do that in a half module. So the industry driver was smaller package size, more processor IOs. We need more throughput within a 3U slot. The nano RF and SMPS higher density RF interfaces were introduced into 67.3, a revision of that standard that's in process right now. There's higher density MT packaging that's being implemented as well. So you can see it affects multiple standards. 67.3 revision, 66.5 is where we're putting all the float on the backplane and allowing these hybrid modules to be documented. And they will go into slot profiles within 65.1 and get proliferated through the market. So the standards part of that, I thought it'd be interesting to take a look at the start of VPX within VIDA, where we were, and just purely from an interconnect standpoint, and look at where we've come and over the last 10 plus years. So the original VPX standard, if you look at 2006 to 2008, VIDA 46 is the basic foundation standard. So this defines the architecture from an interconnect standpoint. It defines the connector, the digital connector, and the guide hardware that go with that. We also had mezzanine. The XMC connector was launched at that time, and FMC. So we had the foundation, we had the digital connector, we had the framework, we had the mezzanine solutions for that. In the next 5 years, RF modules came about. So we documented RF modules and optical modules. RF was the SMPM 4 and 8 position. If you were using a half module, you used 4. If you used full module, you used 8 positions. They were predefined, they were in those spaces, and they all supported the 0.8-inch slot pitch at the time. From an optical module standpoint, there were actually 3 optical termini in the original modules that were standardized. 66.1 had an MT ferrule, 66.2 had a mini expanded beam terminus, and 66.2 was an AirInc 801. Now, the only one of those that's really gone anywhere and moved forward and has been adopted is MT, so because of the fiber density. XMC 2.0 was released as a more rugged connector with multiple points of contact. Aimed at higher speed than the original 42 XMC. And then the power supply connector, the VIDA 42 power supply connector. Jerry showed some power supplies yesterday. That's the connector on those. So the next 5 years, we had a hyperboloid contact variant of the VPX connector come out. 67.3 came out. Now this was pretty revolutionary because we took the float that was on the plug-in contacts in the plug-in module, put it on the backplane. So what that does is allows you to eliminate cables from your plug-in module, directly terminate to the board. It also kind of paved the way for what we're doing today with the hybrids. 67.3 also said, okay, we're limited to an 8.8-inch pitch today. If we increase to a 1-inch pitch, which many applications are 1 inch or more, we can get more space within the module, more contacts, more density, because we've got a larger working space. So 67.3 was released. The MT half module kind of straggled along and was released in 16. The FMC Plus came out with more points, a higher pin count and higher speed. A sealed power supply connector was launched last year. And then when we look outside the box, typically a lot of the circulars, the 3899s, are used in our systems. This was a higher speed, higher density circular connector that got released in VIDA 76. So if you look at today, there is a ton of standards activity around connectors. And if you look at all these categories down the left, this is what we have in place. And if you look on the right, the higher data rate, higher density, higher power, you're seeing those trends come to life in the interconnect standards that are being developed today. So 46.30 and 31, I talked about the higher speed VPX connectors. The higher density RF 67.3, the SMPS and nano RF are getting adopted. In the optics world, where we had that single MT and a half module, we have 66.6, which is putting 2 and 3 MTs in a half module. So we're getting a lot more density in that smaller space. And 66.5 is where we're bringing the options for hybrids into that. And the edge-mounted transceivers that you saw, that'll be part of the solution set for under 66.5. With the XMC connectors, we've got a revision of 61 that'll include higher speed XMC options. We also got 88, which is XMC Plus, which is also addressing higher speed. And then in the power area, 270 volt is becoming more predominant. So we've got a variant of the 62 connector for 270 volt. We've got 3-phase. And on the outside of the box too, and this is really heavily driven by SOSA, is we're looking at, we're putting MTs into circular connectors for outside the box. Get that get that optical fiber density outside the box to go box to box. So if you look at the bottom sentence, the window for next-gen interconnect standards shrinks with each generation. VITA 46 came out in 2000, it was qualified in 2006. The standard was launched in 2007. 10 plus years later, we're doing the next-gen speed connector. It's going to be a lot less than 10 years for that next iteration. So how do we accelerate next-generation standards? So we can build on existing interconnects. So the MT is a ferrule that's defined in an IEC standard. It didn't come from the VITA world, but we're adopting it and packaging it in many different ways, whether it's modules, transceivers, or in the I/O outside the box. We can leverage commercial solutions. So if you look at the VPX connector that came out in the original VITA 46, it's a multi-gig connector. So multi-gig was a TE product line. RT1 was never part of VPX, but it was the original variant of it that was used in data centers and used in high speed. So I put the quotes around it because that was high speed at the time. So it's not used in data centers anymore. I think there's a few legacy programs with Cisco and HP and stuff that are just barely supported anymore. But that connector at the time had a legacy behind it, had a lot of work done on the engineering side, on the signal integrity side. So that was packaged into an RT2 specifically for VPX. RT2R came out to be more rugged. RT3 came out now for higher speed. So we can leverage what's done in the commercial world, and typically the datacom world is 1 or 2 protocol revolutions ahead of us in terms of speed. So if we can leverage what's already been done there, bring it into our market, we take advantage of the volumes and a lot of the engineering work that's been done on the front end. And then we want to establish building blocks. So the nano RF came about because we wanted to shrink the size of RF. We didn't really see anything apparent that absolutely met all the needs of our markets. So we developed the nano RF, and we built the 67.3 standard around solution sets. So if you look at 67.3, it doesn't say you have 4 positions, you have 8 positions. It doesn't define what that is within a module. It just tells you, here's a contact, here's the interface, here's how it can be used. And within 65.1, we're documenting how those configurations are established. So building blocks give you that advantage that you've got a product that can be used over multiple applications. You've got a technical solution that can be used in multiple different packaging schemes. Building blocks, while they're valuable, I mean, if you just look at the slot profiles, you put a P0, P1, P2, you've got connectors that are used, and all these slot profiles use a range and a lot of common modules to build those solutions. So it's a valuable way to approach it, especially in a market that you can't economically tool every variation with all custom components. So building blocks are valuable. You can keep using them in different applications. But when is multiple configurations too many? So if you build a VPX store in Manhattan and you've got slot profiles going up the walls to the ceiling, then we've probably gone a little bit too far, right? Okay, so I want to show an example of that because 67.3 does allow a lot of flexibility in the use of the contacts and where the MTs can go. This is an effort that we did with a few key industry leaders within the SOSA group, and I have approval just to share what this concept and what we've done in that group with you. But we were looking at different use cases, and whether you're using RF in a tuner or a digitizer, you've got different RF lanes that you need, you got a different level of RF performance you need. So some of the key industry leaders, we got together and said, okay, what are the requirements? And we laid out all these different modules, configurations that we could establish with RF and in some cases RF and optics combined. So again, we're looking at how do we take this whole array? How do we limit that? SOSA wants standardization. They want a few key modules, just as it was mentioned yesterday about slot profiles. We're taking the hundreds of slot profiles within VITA and focusing on a very few set, a smaller set. How do we take that and package these into just common modules that the majority of the industry can keep using over and over? This is what we came up with out of that solution set. I am missing, there's one full module with RF with SMPS solution that I'm not showing here, so I'm really just focusing on the nano RF solutions that we developed for this, but it's just an illustration of how we can take many different variations and standardize them. And you can see on here we've got 3 half modules, you've got 2 full modules. The half modules, those configurations, like this 5 RF over an MT is used in one of the full modules. The full modules have 2 separate floating inserts within them, so you could have edge-mounted transceivers side by side, and that float's taken up independently within each transceiver. So we purposely do that, so we have the float. We have the advantage now of economies of scale because we're building the same modules. We have the advantage of the inserts on the half modules being used in the full modules. So from a manufacturing machining standpoint, we can manufacture more blocks of the same configuration. This is a great example where industry came together and said, not everybody's going to get exactly what they want, but what can we do to standardize and bring together a smaller solution set and build that scale. So I'm going to talk a little bit about what will drive next generation standards. Speed, certainly. So we talked about 25 gig, 200 gig Ethernet, PCIe Gen 5 are right around the corner. So we don't like stop at RT3 and say, okay, let's wait to see what's next. There's already work being done there. So what's that going to look like? We talked, yesterday there were some talks about transceivers doing 25, 28 gig, increasing fiber counts. Next generation copper backplane connector, what's that going to be? We've been following VPX, working on intermatable solutions to the VPX connector today. At some point, where do we migrate to get that next generation of speed? This is Strata Whisper that's shown in the bottom right. It has cabled solutions, or we're going to have to start cabling on the backplane rather than running all our traces through the backplane to get the signal integrity performance in copper at those data rates. Density, so how do we get more density? So we saw the nano RF and the optics and how we can integrate them. In the upper left here is a 3U slot. But we have slimmer guide hardware that can free up more space. You can see the guide modules on each of the ends take up some room. There's a little bit of room on the P0 that could be shaved off. The VPX connector was developed for a 0.8-inch slot pitch. So as we look at 1 inch and higher, is there more room that we can take advantage of to take advantage of the 1-inch slot pitch and get more I/O? One of the key things is getting more pin density. We keep hearing that. How do we get more differential pairs out of the same amount of space? So that's things we can look at. The upper right is from Reflex Photonics. Arlen presented this yesterday, and you can look how it progresses into a stacked transceiver, so we can get more and more optics and active optics on the edge of a card. And then within the card, things like optical flex can help with routing in very tight spaces and help your fiber routing. And then rectangular versus circular I/O. When do we get to a point on the outside of a box where maybe circular doesn't have the same density as a rectangular solution, and we may have to look at other options there. Size. We heard a presentation from Ivan yesterday about small form factor. We know there's activity within the SOSA organization, a task team looking at small form factor applications. So for smaller UAVs, CubeSats, smart munitions, what's going to be that next standard architecture? So this is exciting. It's relatively early, and but it's going to be definitely a focus for the interconnect challenges moving forward. And then power. So with the increase in electrical systems and voltage is increasing, we're seeing 270 volt applications pretty common in a lot of avionics applications today. There's 600 volt ground vehicles systems available. that are coming. The 1,000 volt, if you look at 1,000 volts or more, some of the laser weapons, things like that generate a lot of power, a lot of voltage. So what are those interconnects going to be? So that's another area that's kind of on the accelerating very fast and is going to have to be looked at very soon. Final slide, standards development is challenging. Some of us that are involved in standards every day, it's actually quite exciting, but it can be painful. But it's needed to support the emerging technologies, to build that ecosystem, and to be a vital part of the industry development that we have today. And it's never been as active as it is today.